Welcome back. Today we're going to be looking at the Hiwatt DR103 bias circuit. We will not actually be implementing the circuit into my amplifier today, nor will we be doing basically any math. We're just going to go over the concepts behind the stock bias circuit as well as the voltage doubler. This is an example from the hiwatt.org website of how you can implement the voltage doubler circuit. I highly recommend checking out that website if you are curious about this modification. Today we are going to walk through why we need bias for our power tubes, what that does. We're also going to look at the concepts behind how current flows through the stock bias circuit, how that happens through the voltage doubler circuit, why you may want one or the other, and then also look at LTspice simulations for each of those two circuits. On our next video, we're going to actually implement that voltage doubler circuit into my Hiwatt after I also change out the power tube sockets and output transformer. We will first measure the stock circuit and then implement the voltage doubler and hopefully get some sound tests of a nice working Hiwatt DR103. Okay, so let's go ahead and jump into the bias circuit for these amplifiers. Okay, so before we dive into the actual bias circuits, it may be worth looking at a schematic for the Hiwatt DR103 and taking a closer look at a power tube here. This is a EL34 based amp. And we can talk about why we need a bias circuit at all. Basically, what's going on here is we have, if this is our power tube, it's called a pentode because there are 5 separate nodes: the plate, the cathode, and then the grid screen, and the grid, and then the other screens here. These are all called grid screens, but usually it's G1, G2, G3, or some combination of those. Okay, so this most positive point of our amp is going to have a built-up positive charge from our B plus supply. This is the most positive point, usually somewhere around 400 volts or so. And then down here, we're going to have a buildup of electrons, which are negative. Now, these electrons want to do everything they can to get from here up to here. And if we didn't have bias, if we didn't have a negative voltage here to throttle them, they basically would just go full charge all the way up at full speed and just no throttling at all of how many electrons would flow, which would burn up our tube, and we don't want that. We want to have some kind of control, some kind of way to manage how many electrons are flowing at any given time. And the bias basically creates the resting rate of that, which we call the quiescent current or resting or idle current. So let's see how that's happening here. We can see that our bias is being fed in from this point and then is going to, it's split between these two 100K resistors. The current is going to travel up and to that grid for each of these. Now, the input, this is coming from the phase inverter, is going to be split positive alternations on one side and then negative on the other, and is going to go to a pair, or if this were a 50 watt amp, there would just be one of these tubes and one of these tubes. And then same on the other side, the bias voltage is applied here. Current will then travel through that 100K and then be divided to these tubes. I would say equally, but that's in an ideal world. Really, it's based on the demand of each tube and what their individual gain values are within the range of the tube set. Okay, so let's take a closer look now at the actual bias circuit. Okay, so in the same document, we are looking at the Hiwatt DR103 power supply. Everything up here, this is where you plug into the wall, going through our power transformer. These two sides are part of the same power transformer. It's just split up to show the difference between the two functions of the circuit. We are creating DC power here. This goes to HT supply, which is high tension, which is another name for the B plus, or the power that's going to your power tubes and your preamp tubes to supply power to those at the plates. But down here, this is what we're interested in today. This is the bias for our circuit. So let's zoom in and take a closer look at what's going on here. Okay, so in this amp, we're going to have roughly 50 volts AC at this point. Now, because that's AC, it's going to go above and below zero at 60 hertz. So on the positive half of that, right here, we're going to have positive here, negative there. On the negative half, we will have negative here, positive there. So that creates two different situations for what's going on. This is a half-wave rectifier. There's only the one diode here. So only the negative alternations are going to come through, which is how we get a negative voltage over here. So let's take a look at what happens on our positive side. When we have positive here, we'll just go ahead and erase these so it's not confusing. Okay, so with positive here, our current is going to flow to this point through the resistor, and then it gets to the negative side of this diode, and this diode is basically going to act like a check valve. We will not get anything on this side. So this entire half of the waveform is not going to be used. We're only going to have the negative. Okay, now let's look at the other situation. What happens when we have negative here and positive here? And keep in mind this is decoupled because it's through a transformer. It doesn't matter that there's ground here. We're just looking at that positive is not necessarily a positive voltage. It's just more positive than this point. So it's okay that this is connected to ground. Okay, so in this point, we're going to have negative and then positive. So if we're still using conventional flow, we would then charge up this cap. We would have current that flows through this resistor to go to here. The negative side, because this side here is now more positive than this side, we're going to be able to flow through this guy and have a full circuit. And we need a full circle. We need to go from positive all the way to negative in order to have current flowing. Now, because of that, we're going to get negative voltage at this point. So before we take a look at the simulation, let's take a look at the voltage doubler circuit and how this is different. Okay, so we are now looking at the different configurations that are available for bias circuits. This document is available on the Hiwatt.org website, drawn up by Mark Huss. We can see we have the stock DR103 circuit, stock DR504 circuit, pretty similar. And then we have our modified circuits for the 103 and for the 504. We're going to be looking at this one here for our analysis. These two are the same. This one just makes it so that we have separate bias control for each of the two sets of tubes instead of one bias for all of them. This one's arguably more functional, but they functionally operate the same, just with this part of the circuit doubled. Okay, so let's take a closer look at how current is going to flow in this scenario for our positive and negative alternations. We have positive here and negative here. Current will be blocked from going through this diode, but it can get through this side. And remember, it wants to get back to here. Okay, so it's going to flow down through that diode. These points are not actually connected. This is a gap in the wiring. So it's going to come around here. And because this is the more positive side of this electrolytic capacitor, this capacitor is going to get charged up. Now at that point, this capacitor, as it's still charging, will allow current to not actually flow, but seemingly flow from one side to the other. which means we're going to have a complete circuit. It's going to go back to there as this capacitor charges up. If this capacitor is fully charged, current will no longer flow through that. It'll just stay at whatever voltage it wants to be at. But we will still have a small proportion of current that travels through here to then go back. And similarly, some will go up here. Some will split off in this direction, depending on the resistance and the setting of our bias pot to come back to here. But remember, it wants to get back to this negative point, so it's actually going to come this way. And this capacitor will not be charged. Okay, so now let's look at what happens when we have the other side of the sine wave. And let's keep in mind that this capacitor is charged up. So it has positive and negative here. So at this point, we're going to have negative there. So we're going to have current that flows through this side. We know that. But our positive is going to go through here. It's going to charge up this capacitor. And same deal, some's going to go back through there, and then it's going to make its way back through this. Some current will go through here. Some will split off to go through all this, same as before. And then it will all recombine back at this diode to get to where it wants to go, the negative point here. But as that is happening, what's going to happen with this other capacitor, it has charge, and it now sees a path from positive back to this negative. So this capacitor is now, instead of acting like a load, is going to act like a source. And it is going to, because it's not being charged actively, is going to discharge. And it'll actually, a small proportion will fight with that flow here. We're going to have a little bit of a fight there. And the way that works is just the larger current will win and choose the direction the current is flowing. But we can see all these other ones where the arrows in the same direction are going to add together. Which means we're going to get an effective doubling of the power available at our bias here. That's why this is called a voltage doubler. We're going to basically create a situation where we charge up a capacitor on one cycle. On the next cycle, it then is able to discharge. That stored energy then aids in creating a higher voltage at our bias output that is here. That's all going to change based on what's going on with these. What's up with the setting here, how much determines how much voltage we have at our bias point. Okay, so now let's take a look, now that we have an idea of how the voltage doubler at least conceptually works and why it might be an improvement. Let's take a look at some simulations in LTspice to see if this holds true. Okay, so we're now in LTspice. We're not going to go too deep into what LTspice can or can't do, at least in this video, but we are going to look at simulations of the stock circuit here, and then we actually have to have two circuits for the modified voltage doubler because we can't really easily accommodate for a potentiometer in LTspice. So this circuit here is with the potentiometer all the way one way for the bias adjustment. This is with it all the way the other way. You can see this 22.448K resistor is kind of a funny value, but that's just the two resistors in parallel for what we would otherwise have in the circuit. Okay, so let's first simulate this one, and we're just going to use this as a gut check to see what voltage we would have at the bias point for each of these, and see if this voltage doubler, in theory, will double the voltage. So if we run this simulation first for the stock circuit, and then measure right here, okay, we can see we start at 0. This curve here is the time it takes for this capacitor to charge to then get up to operating voltage. During that time, our voltage will be rising in a negative direction or decreasing, however you want to think about that, to settle out at its DC point. But we can also click here and see, okay, so we go from 0 volts, it'll settle at negative 41.8 volts, which is pretty dang close to our schematic negative 38 volts, especially since this is unloaded, so it will be slightly higher than what will actually be in the circuit when this is connected to a load. Let's now take a look at this guy and run a simulation. Okay, so we can see a little bit different, but not too much. What do we have here? Okay, negative 41.803. So that side of the circuit is basically exactly the same as the stock circuit that we had here. Now, what about this one? When the bias pot is all the way the other way. Okay, a little confusing to see which one's with which. This guy, sorry, this one is for here. Let's run this again. Okay, so this is this one. That's this guy. And then here is our other one. Okay, so stock, we are looking at negative 41.78 volts. This side of the modified voltage doubler, negative 41.879. So we're within not like tenths of a volt, right? Okay, and then this one, you can see we have negative 71.31 volts, which means we can run the tubes at a colder bias. So we can get as hot, basically, as we otherwise would get, a more positive voltage, but we can still throttle the tubes and run them closer to cutoff to save them from being in a situation where we're going to get a thermal breakdown of the tube. We can go all the way up to negative 71. Now, I doubt you would want to go this high, but this does give you flexibility in terms of accommodating for modern tubes that are not constructed to the same level of reliability as tubes from the 1974 Hiwatt era. So this gives us some flexibility to ensure that we're going to run our tubes safely and operate them at a proper bias level. In theory. So this is the theoretical version of these circuits, because this is a simulation. The next step to prove that this is a good circuit would be to build them. Okay, so the next step I was going to take was going to be to build these circuits isolated on the workbench, build the stock circuit, powered up with my Variac at 50 volts AC, and measure the bias in DC volts on the output. However, I was getting much higher values here than I expected. Even with only 40 volts of AC applied at this point, I was getting close to negative 50 volts DC at our bias, and that was even after adding a 390K resistor between these 2 points to simulate the grid to cathode resistance of a single tube. So I think what we're going to have to do is instead look at these in the actual amp. I will, before applying the voltage doubler, get everything else fixed on the Hiwatt. We will then measure the bias, see where it sits. I will then show you how I'm going to implement the voltage doubler circuit into the Hiwatt amp. And then we will again measure the range of bias values that are available. Now, it could be in your Hiwatt you don't feel like you need to do this. You're okay with having a fixed, non-adjustable bias. I would argue that most of us could benefit at the very least from a modification that allows for a variable bias, changing out this resistor with a fixed limiting resistance, as well as a trim pot that can allow this value in DC to be adjusted for modern tubes. Again, you will potentially run hot because that will only limit you down to a hotter bias point, whereas the voltage doubler will allow you to go colder and potentially not have to bias your tubes above 80 to 90% dissipation. But let me know what you think. Do you have a Hiwatt that doesn't need this, that is just fine with the stock bias circuit? I am genuinely curious to hear how people are running their vintage Hiwatts these days, because I'm going to be using mine a lot once it's up and running. So until next time, I do have the output transformer on its way. It should be here this next week, so we'll be diving back into finishing up this Hiwatt amplifier and doing some sound tests very soon. But thanks for watching, and let me know if you have any questions or want to see anything else in terms of the concepts of how these bias circuits work. Have a good day.